Now let us quickly see how we can determine these sampling points and their corresponding weights. Now consider a function that passes through n points, at each of which its value is given as phi ri. So this is a known value. We can write such a function that passes through the points Ri and attains a value of phi Ri at those points as a function psi r equal to L1 phi r1, L2 phi r2, where L1 is 1 at r1 and 0 at other r's. So L2 is 0. So uh, so psi r1 will be exactly equal to phi r1. Similarly, L2 is equal to 0 at r2, is equal to 1 at r2, and it's 0 at r1. So psi r2 will be equal to phi r2, and so on. That is, phi ri will be equal to psi ri at every I. So this is the property that each of these LJs must satisfy. Now we are hoping to integrate this integral, and this integrand here is determined as, it can be written as psi r plus a correction term. Now, already we know that phi r1 is equal to psi r1, and so on, phi ri is equal to psi ri. So at the points r1, r2, etc., we have already satisfied the fact that phi r and psi r are the same. So this this function pr therefore has to be such that at r1, r2, etc., this correction term goes to 0. So pr makes them go to 0. So pr can have a form like this, where pr is equal to r minus r1, r minus r2, etc., where at each of these r's pr goes to 0. Therefore the correction term vanishes at those r's. Now if I want to integrate phi r, I'll integrate from -1 to 1 phi r dr, which now can be written as j equal to 1 to n phi j minus 1 to 1 lj dr. So that's this equation. And then I add this integral due to this correction term, which includes these betas. So beta j, it goes from 0 to n minus 1. So it includes this beta j, so beta 0, beta 1, etc., and r to the power j times pr dr. Now consider the situation at some special r's. Consider the fact that if this is 0, if this is 0 at some special r's, then at those r's, this integral will be exactly equal to these summations. So at the special r's at which these are 0, these integrals are 0, we have we have the fact that this integral can now be represented by a summation, where phi j is the value of the function at rj, and we call this quantity the weight wj. So j equal to 1 to n, phi j wj will be true when this integral is exactly equal to 0. So that's what we try to impose. We try to impose for j equal to 0 to n minus 1, pr to the power rj dr is equal to 0 for all these j's, and then we can write this integral as a summation of the values of the function at rm times the weights. And what you can immediately see from here is that this is not correct. This is correct. Okay, I'll correct it in the notes. What we also see from here, that n-point Gauss quadrature will yield exact results for polynomial functions up to the order 2n minus 1. So if n equal to 1, then 2n minus 1 is equal to 1. So first order Gauss quadrature, single point Gauss quadrature will exactly integrate linear functions only. We have already seen that for n equal to 1, r is equal to 0, r1 is equal to 0 and w1 is equal to 2, and this is exact for linear polynomials. For n equal to 2, it will be 2n minus 1 will be 4 minus 1 equal to 3. So up to cubic polynomials will be integrated exactly for n equal to 2 and so on. So now let us see for a particular case when we are doing two-point Gauss quadrature, what are R1 and R2, how do we determine them? So for n equal to 2, you will have two such equations. Firstly, for n equal to 2, you will have two sampling points. Let's call them R1 and R2. So you will have R minus R1 and R minus R2. So this will be your PR, right? And then you have two such equations. One would be minus 1 to 1 r minus r1 into r minus r2 times r to the power 0, that's 1 dr equal to 0. This will be your first equation, and this is for j equal to 0. For j equal to 1, you will have the same function multiplied by r to the power 1, that is r dr equal to 0. So these two equations, if you solve these two equations, you will get a solution, and it's possible to solve this quite easily. The solution would be r1 is minus 1 by root 3 and r2 is 1 by root 3. So at these two special points, this integral will boil down to this summation. For n equal to 2, it will boil down to this summation where the phi m's are phi at r1 and phi at r2. We still have to determine the weights w1 and w2. If we sum them together, this will be equal to minus 1 to 1 phi r dr. This will be equal in cases where phi r is a polynomial of order 3 or less. It will be approximate for polynomials of higher order than 3. Okay, now how do we determine w1 and w2? So remember, wm is minus 1 to 1 lm dr, and lm is a function that is 1 at the mth point and 0 elsewhere. We have only 2 points, so on the r-axis you have r1 and r2. So the r-axis is defined between 1 and minus 1, and your r1 is minus 1 by root 3, r2 is 1 by root 3, and this function L1 is 1 at r1, 0 at r2, so it has to be a function like this. This would be your L1, and L2 will be a function which will look like this. So these functions can be easily found out, and these functions are these. So this is a function which at r equal to r2 will be 0, at r equal to r1 would be 1. This would be at r equal to r1, at r equal to r1 will be 0, at r equal to r2 will be equal to 1. So these are the two weights, and if you now integrate them from minus 1 to 1, you get 1 in both cases. So the weights are 1, and therefore the integral minus 1 to 1 phi r dr is approximately equal to 1 phi evaluated at minus 1 by root 3 plus 1 phi evaluated at 1 by root 3. It is exactly equal if this is a polynomial of order less than equal to 3, and it is approximately equal if it's greater than 3. So, so that is how you determine R1 and R2, and once you determine that, this is how you determine the weights. Now this was rather easy for n equal to 2, but if you want to do it for higher n's, then it's a bit difficult. So I have given you the table here. These points have been determined. So for order 1, there is only one Gauss point, which is at 0, and the weights are 2. We have already seen that. For 2, the Gauss points are 1 by root 3, which is this, and minus 1 by root 3, and weights are 1 in either case. In 3, these are the Gauss points, these are the sampling points, these are the weights. Similarly for 4, you can go on like this, and there are functions, MATLAB functions, which give you Gauss quadrature, Gauss sampling points and weights for any order quadrature. But we don't need more than order 5 or 6, and for our course, this table will be in most cases sufficient. Now let us look at this rather simple problem. This is your phi r. It's a cubic polynomial. So 2n minus 1 is equal to 3, which implies that n is equal to 2. You have to do second order Gauss quadrature, 2-point Gauss quadrature, and that will integrate this exactly. And the exact integral also can be easily calculated, and we've calculated it here for you. So the exact integral, if you do this exactly, is this. Now 1-point Gauss quadrature will give this as 2a naught. For 1-point Gauss quadrature, remember the weight w1 is equal to 2, and the function has to be evaluated at 0. So if you evaluate this function at 0, you get a naught. So this is equal to 2a naught, which is only the first term, of the integral. If you now evaluate this for 2-point Gauss quadrature, let us take p is equal to 1 by root 3. So for the first point, phi r1 is equal to a0 plus minus a1 into 1 by root 3 plus a2 by 3 minus a3 by 1 by 3 root 3. This is phi r1, and the weight for this is 1. So this is the term. For the second, you have to do phi r2, which is equal to phi 1 by root 3, which is equal to a0 plus a1 by root 3 plus a2 by 3 plus a3 by 3 root 3. That's given here. So if you add them, you get the exact value of the integral, as we of course expect for n equal to 2. The third order integral should be exactly evaluated. So that's in 1D, and if you want to take this to 2D, then this is what you have to do. So we have to do this differently for rectangles and triangles. For rectangular elements, for quadrilateral elements, they map into the isoparametric square, which runs from -1 to 1. So Ke is evaluated as in 2D from -1 to 1 B transpose CB J dr ds, as we have explained before. In 3D, this would be -1 to 1, -1 to 1, -1 to 1, triple integral B transpose CB J dr ds, let's say dt. So this would be in 3D. In 2D, this would be the case, and this is integrated now with the Gauss formula for 2D integration over rectangular and square domains, as choose the order n, then I equal to 1 to n, j equal to 1 to n, wi, wj, phi, ri, rj. So for this quadrilateral, if you do a 2-point integral, you would go back to the table for the first, for n equal to 2. So your sampling points are 1 by root 3 and minus 1 by root 3. Weights are 1. So you will now get uh, 2 to the power 2 sampling points. So you will get total 4 sampling points. And in 3D, you would get 2 to the power 3, that is 8 sampling points for 2 second order Gauss quadrature. And what would the effective summation be? Summation would be I equal to 1 to n, j equal to 1 to n, w1, w1, phi, r1, r1. That means you will have w1 is 1, this is 1, phi r1 r1 is phi at evaluated at minus 1 by root 3 minus 1 by root 3, that is this point. Okay, then plus w1 w2 phi evaluated at minus 1 by root 3 and then 1 by root 3, so this point. Similarly, plus w1 w2 phi, let's say 1 by root 3, 1 by root 3, which is this point. And finally w, this is w2 w1, and then finally w2 w2, which is phi 1 by root 3, 1 by root 3. This is this and that, sorry, this is this point, and this is this point. So that's how I've written. These 4 terms will make up the Gauss quadrature formula, and the weights and the sampling points can be taken from the 1D table. Recall that for triangles, the parent is given by this right angle triangle RS, and this is the parent triangle with points given by 0, 0, 1, 0 and 0, 1. And now any function gxy to integrate over dx dy with the domain is VE, the domain of the physical element. If you make a change of variables to dr ds, so this has to be replaced by j dr ds like in the rectangular case. But the domain of this integral, so if you take a small element here which has dr and ds lengths, so r will go from 0 to this is r equal to 1 minus s. The equation of this line is r equal to 1 minus s. You can verify that. So r will go from 0 to 1 minus s, while s goes from 0 to 1. So if you scan that way, you will get the entire integral. So this is what the new domain becomes in the parent coordinate system. And this is not minus 1 to 1 as in case of the rectangle. This can still be converted into a weighted sum. So this whole thing GRS times J evaluated the sampling points weighted by WI summed together will give you this integral. Now we know that for triangles to denote a point we sometimes use area coordinates. So this point has RS and its area coordinates would be RS1 minus R minus S. These would be its area coordinates. Let's call them zeta 1, zeta 2 and zeta 3. So if you use zeta 1, zeta 2, zeta 3 coordinates for first order Gauss quadrature, your sampling points are 1/3, 1/3. So zeta 1 is 1/3, zeta 2 is 1/3, and zeta 3 would be 1 minus 1/3 minus 1/3, that is 1/3 as well. So this would be your first order Gauss quadrature. And single point first order Gauss quadrature. If you want to do second order, you have two options for triangles. Again, you can evaluate it at r equal to 2/3, 1/6, 1/6, 1/6, 1/6, 2/3, and zeta 3 comes out as usual from 1 minus r minus s. So in this case, the weights are 1/3, 1/3, 1/3. You have another option where you can evaluate it at half, 0, 0, half, 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 and again 1 minus r minus s comes out as in each case, and again the weights are 1/3, 1/3, 1/3. We seldom need more than third order Gauss quadrature over triangles. One thing that you should note is in a triangle in 2D, you don't have n square terms in the summation. You have 3 terms. So in fact, this table explains it. For second order Gauss quadrature, for example, you have two options. First is this, the order, the number, the sampling Gauss quadrature order is 2. The number of sampling points is 3. It would exactly integrate polynomials of the order 3. These are the sampling points and these are their weights. Similarly, this is another set of sampling points and these are the weights. And this is also for second order Gauss quadrature, and you integrate polynomials of the order 3 exactly. For 3, the number of Gauss points are 4 and they are shown in this parent element here. You can integrate up to order 4 exactly, and these are the weights and sampling points given here. So we seldom, as I said, you seldom need more than n equal to 3, and therefore we will stop there with the triangular elements.